Hi, I'm Connor DiMatteo.
I'm George Karyazis.
And I'm Caleb Morgan.
And this is the self-sustaining hydroponic greenhouse with photovoltaic power and optical sensing. We are Group 5, and our problem statement was to solve the problem of community gardens and accessibility within municipalities. So we decided to invent an automated greenhouse system that can be used in localities to create community gardens by eliminating the need for people, resources, and knowledge to grow produce within a city. Following the project introduction, we wanted to give you a brief walk around the greenhouse to showcase our 5 subsystems, including the rainwater collection system, power generation system, nutrient pH deposition system, the hydroponic technique employed, as well as the PCB and control system we use to automate the greenhouse. We had several goals in mind when constructing it, including the ability to encode plant profiles, keep it compact, keep it affordable, filter out any contaminants from the rain, generate our own power using solar energy, as well as being able to have interconnectivity and power control using a website. And here you can briefly see some of the core advanced and stretched goals and objectives kind of separated out into the different subsystems that we've included here. With this slide being a continuation from the last slide, concluding all of the goals and objectives that drove the design and construction of this system. We then took those goals and objectives and turned them into the specifications shown in this green table here, which we'll sort of outline and showcase throughout the rest of this demonstration, as well as the system functionality block diagram shown to the right, which is kind of showing how the system makes autonomous choices when it's making sure that it's able to function without a human present.
So here's our rainwater collection unit. It's composed of 3 containers to store the water that's all being fed by 2 gutter channels located on the side of the greenhouse. A 3D printed mesh filter prevents lots of the larger particulates from entering into our water storage. We have the system monitored by a float sensor to let us know if it's ever running low on water to ensure that we have time to supplement our own water in this case. All of these containers are being connected underground through PVC to ensure that they're properly being filled and dispersed into our systems evenly. Water from the rainwater system is then filtered and delivered to its respected unit. During this process, water is primed and sent through a diaphragm pump triggered by the system when running low on water and powered through a relay. This pumps the water through a fine mesh filter and then through a sediment filter. We then have it set up to go through 3 different carbon filters to ensure purity of water and through a UVC tank to ensure the water is at its purest form before diluting it with different pH and nutrients required by the plants. A solenoid is also added to pump to a specific system once all 3 systems are finally built. To ensure the purity of the water, we decided to use Raman spectroscopy to analyze the water and ensure its purity of heavy metals and other particulates. We did this using Stokes Raman spectroscopy composed of a 785 nanometer laser excitation source and Ocean Insights Raman spectrometer. We used an SMA and a FCPC multimode fiber through multiple lenses and filters, all designated and located inside of a 3D printed enclosure to be able to use Ocean View to ensure that the Raman shift that we were observing was that of pure water.
Following the Raman spectrometer is the system-specific reservoir. In the video on the left, we're showing how when we update the system with a new plant profile, it immediately triggers the output can on the left-hand side, which is pumping that nutrient pH balanced solution into the nutrient film technique system. On the right-hand side, that is showing the inside view of the greenhouse immediately after we triggered the system. You can also see here how the water is recycled back into the sub-reservoir. Each system-specific reservoir will feature an ECTDS sensor, an optical pH sensor, a water level sensor, a submersible water pump, and featuring a naturally circulatory design in which the right can acts as an input and the left can acts as an output, so that as the water pumps into the nutrient film technique system, it comes back down into that right side and flows underground to create one full cycle. We can also see the peristaltic pumps pumping in balancing solutions.
When our system sensors detect that our pH or nutrient levels are out of range, peristaltic pumps add solution to bring our values back into our specified range. Our EC/TDS sensor has a range of 10,000 parts per million, which is more than enough for hydroponics. These sensors are responsible for reporting levels to the microcontroller, which then evaluates the levels. Our pH sensor has the full range of pH 0 to 14. This sensor functions similarly to that of the EC/TDS. Peristaltic pumps are powered for 20 seconds whenever the sensors report invalid levels. This adds about 33 milliliters of solution to the subsystem reservoir.
So here's our hydroponic structure. It's a nutrient film technique structure. Water from the sub-reservoir is being pumped into the system, already pH and nutrients balanced, and then water is cascaded down the two levels, supplying the plants with the proper nutrients and pH needed, as well as water, to ensure great harvests for us. After this, the water is then taken out of the system, back into the container to be rebalanced and used again to the plants. We made sure that the dimensions of this hydroponic greenhouse were in our specifications to ensure that we had enough space to fit 3 of these whole systems inside of our greenhouse once everything's completed.
Greenhouse wouldn't be complete without our photovoltaic power generation system, in which we feature two 100-watt monocrystalline solar panels attached to a hand-constructed frame along a 30-degree angle relative to the ground. We have that passing through a solar charge controller to regulate and monitor the amount of charge we're getting into a 12-volt DC battery. And that DC battery also features an AC inverter on there as well for some of our AC necessary power systems, including the UVC filtration system. And then in order to bypass the circuit, we also used a relay that's attached directly to the battery.
Here we have our PCB. On the left we have our PCB with all our components installed for a one hydroponic system setup. On the right is a rendered image of the same PCB. The PCB has two separate voltage levels, 12 volts for power to the driver loads and regulator, and 3.3 volts from the regulator to the remaining PCB components. Here we have our two microcontrollers. On the left is our ESP8266 as well as its programming pins, and on the right is the MSP430 as well as its programming pins. This slide shows the liquid level sensing circuit, which includes two multiplexers for pin conservation on the left. On the right we have our connections for our remaining EC/TDS and pH sensors. The pumps are controlled through the use of low side drivers as shown below. The two microcontrollers, the MSP430 and the ESP8266, perform independently from one another, requiring separate programs. These microcontrollers communicate using UART. Below is a block diagram showing program flow and microcontroller communication. Here we are demonstrating the boot time for the system. This was done by powering the system and seeing how long it took for the watering process to begin. This occurred almost instantly. The website has three main views as shown below. The home view shows all the sensor information. The config view shows all the plant profiles and gives you the option to update or remove them. The edit view is where the actual editing of the profile occurs. The images also show the slight difference in mobile and desktop appearance.
Come to the end of this project, we were able to demonstrate a lot of things, but primarily we were absolutely able to achieve our goals of eliminating the need for people, knowledge, and resources from a municipal government in order to make a self-sustaining community garden. We were able to prove very fast boot time for relatively cheap cost, as well as multiple ways of analyzing the system through TDS, pH, plant capacity and dimensionality, as well as some of the ways we were able to optimize it through the use of optical components such as Raman spectroscopy. In the future, we might do things such as optimizing the system to further reduce the cost, installing additional sub-reservoirs and hydroponic systems, and as well as trying to increase the plant diversity through that installation. Additional weatherproofing to make sure that we can withstand hurricanes, and then, of course, hand constructing future greenhouses to increase our plant capacity.